know, I told you, we measure each and every amount contained in each sieve, and then we try to get the cumulative amount contained, and then later determine the percentage passing each sieve. So percentage passing each sieve is what we plot as sieve size to determine the particle size distribution. Okay. Now, that's the particle size distribution that we get, percentage passing each sieve. This percentage between each sieve, we will just come and, add together plus what is written in the pan, then get the percentage passing, get the distribution. Having known that gravel is up to 2 millimeters, sand is up to that, and anything below that is clay, we would consider that 2 millimeters is around here. Yeah, this is where the 2 millimeter is. 2 millimeter is around here. That means, and then goes up to 0.755 here. Yes, the whole of this is sand. That's the only percentage of clay, maybe around 0.2, 0.2, So the whole of this is sand. This soil is sandy soil. Is sand. All right. Now, for the couple of things that we plot particle size distribution we determine. One is coefficient of uniformity. D60 over D10. D60 would be from 60% the particle size distribution. That gives you the proportion of this that is 60% finer. All right. D30 gives a proportion that is 30% finer. D10 is 10%. So such that the coefficient of uniformity is U, D60 over D10. Coefficient of curvature is D squared D60 over D10. This coefficient will either give you whether soil is uniformly graded, well graded, or poorly graded. Okay. The other parameter that I probably should have put there is the other parameter K that gives you the coefficient of permeability that relates the D squared by a constant C to relate the hydraulic conductivity of sandy soil. The hydraulic conductivity C, K is constant C, D10 squared. D10 squared. So then, in order to find the distribution of the particle size distribution, either sieve analysis or odometer analysis. For odometer analysis, go ahead, Humphrey. Am I still not audible?
It's still breaking a bit, but I just wanted to confirm, what have you said that sees in permeability?
Now, for the permeability, there is for granular soil. Let me come back. The permeability of that soil will be a function of D of the soil. Okay, D10 soil, constant C. That constant C is about 1.
Okay, thank you, sir.
All right. So, am I still breaking?
Yes, you're breaking, but we are following ish.
Okay. I have my mouth as it's possible to my laptop, and I don't know why, but let's believe this will improve us. All right. So for the particle size, for the hydrometer analysis, okay, this is the principle of sedimentation, where the settling velocity is proportional to the diameter of the particle. Okay, so diameter of the particle D, okay, is proportional, because when we have an hydrometer, the way this that you have soil, okay, with water, try to agitate it a little bit, okay, agitate it a little bit, add dispersing agent, usually it's something, I just forgot the dispersing agent, you put it there to prevent the liquid from flocculating, and then put in the hydrometer, then down. Now, the hydrometer sinking depends on the particle sinking. So the length of the hydrometer and the time taken to change, okay, it will be, can be correlated with the particle, okay. Also with the viscosity of the water, the specific gravity of the particles and the density of the water, okay. So the D, the particle size D of the soil, okay, times the viscosity over those constant, the length with the diameter is, sorry, the length of the diameter and the time it takes for that length to change. Right? Able to, read the length of a hydrometer of various times, and you are able to, get the particle size distribution joined together with that to form one large particle size distribution. However, I only use hydrometer analysis always in my life if just getting the particle size distribution of anything lower than that for analysis. Okay, now we said that anything. Let me go back to previous slides. Okay, anything that passes 0.74 millimeter is clay. Anything retained in 7 is either sand or gravel. Okay. These two are known as granular soils. This clay and silt is fine gravel. Now, the difference between the two is that the behavior of this is more or less dependent on the particle size. The behavior of this depends more on the water content. Now, it's very important, very, very important that we understand the behavior of the fine soil based on the amount of water. That brings us to one thing, the consistency of fine-grained soil, and that behavior depends on the amount of water in the soil. When we add water to fine-grained soil, it changes consistency from dry to so its behavior would depend on the amount of water. So we add little water to clay. It goes into semi-solid state, goes to state. As you continue to go, it goes into semi-liquid state. The water content in which the soil changes from solid to semi-solid state is the shrinkage limit. The water from semi-solid state to plastic state is the plastic limit. Water content that is in from plastic state to semi-liquid state is the limit. These three states define the consistency of fine grain soil. Okay. Let's continue and see how things go. Now we determine the consistency of fine grain soil in ArtBook. We define as the ArtBook limits. The liquid limit, which is in which the soil turns from the be determined in the lab from the method. This is what we want to get the ranges. Okay, we prepare soil sample. This soil is sieved through sieve number 40, sieve number 40. Soil sieve number 40. So sieve 40, sieve number 40 is right here, 0.42 millimeter sieve. Okay, that's the sieve that you see. So in other words, this soil contains small portions of sand and fine grained soil. That much is usually affected by the, okay, it's usually affected by the moisture. Okay, sieve the soil through sieve number 40, portion contained in the fine grained soil. What do? You will prepare soil sample at different moisture range. Okay, in the cast graded, cut a groove through, mark this, and count. Give me a second. Now count the number of blow counts required to close this groove. Record the number of blow counts. Take a portion of this soil and take its water content. All right. Do this at different moisture content. Okay. And one. Do this test by putting the water or drying back the soil a little bit. So what I usually do is when I want to dry back this soil, put it in the oven 15 seconds. That's enough to cut down some moisture. Put the soil again in the cast graded device, cut the groove, measure the, do the crown, count the number of blows, and 2, required to close the groove and get water content 2. Test I could do at a different water content, number of blows, water content 3. So I'm going to, the water content is determined, the standard method of determining the water content from the oven. You, by now, you know that. I'm going to put blows N in the log scale and the water content in natural scale, right? Line, straight line, known as the flow. Okay. Put this up, add 25 number of blows. I'm going to a line that touches that line parallel to that, the water content liquid of that soil, the liquid of that soil. So this line defines the flow curve. The slope of this line is known as the index. And that could be determined from any 2 points, the water content, and the number of at those 2 points that you've taken gives you the flow of that soil. Now, you could get an example here, and then you calculate the index of that soil. Okay. Now, for plasticity limit, we're going to, get the same soil, rub it by the palm of our, and our palm sucks some moistures out. All this until it's 3 millimeters thick, and then and measure the water content of those rolls. So the content of that 3 millimeter thick is known as the plasticity limit. The difference between the liquid limit from Casagova and the limit from rolling thread gives you also the index. Now, depending on the plasticity, it either defines the soil to be PI is non-plastic all the way to PI greater than 50, actually it should be 50. That is highly plastic soil. Now, we use this plastic index and the liquid limit to define whether the soil is clay, okay, the portion passing from A, or it's silt. Along with that, with the plasticity chart, and to listen carefully with the plasticity chart. The plasticity chart has 2 lines. One is the A line, given by the equation 0.73 limit minus 20, and the U line, 0.9 liquid limit. What are the differences of the 2 lines? The A line is a line that is between silt and clay. Any plot above the A line is clay. Plot below the A line is silt. Okay. U is the maximum theoretical line. No soil exists above the U line. And I'm repeating that. No soil exists above the U line. Okay. Now, there is an arched portion here where this soil either behaves as both silt and clay. It will behave as both silt and clay, this arched portion. So this portion is clay, clay, below the L is silt. Now at 50 degrees, sorry, not 50, but 50, liquid limit equals to 50, it distinguishes whether high plastic or below 50 limit is low plastic. So in other words, if the soil would be clay of low plasticity, silt of low plasticity, clay of high plasticity, silt of low plasticity. Okay. Any question up to that? Any question? Let me pick some question from you. Okay, I'm Fred. Let me try.
By any chance, if you plot a graph that is above the U line, you know that you have made a mistake somewhere, or this isn't a soil.
That's the soil above the U line.
Pardon me, sir?
Above the U line. Nothing exists above below the U line. Did I make myself clear?
Yes, thank you.
So did you know that fact before?
No.
So that's now known to you. So I'm reviewing actually what you should have done in third year. All right. Let me throw a couple of threads too. We now want to fully classify soil for engineering purposes, not only grading the soil and doing plasticity. We combine gradation and plasticity. Like I told you, okay, if I was working down project, I would go ahead and do the okay. I do not need to do that. I do not need to do that. Part of the distribution plus the ArtBook limits to actually define that soil. If I was working on a dam project where I'm working only on clay, filters for dam project, then I would go and do a meta-analysis. That's we'll get more to go on. Now we need to fully classify the soil. We have various classification systems, but two more common. Okay, unified classification system and let me get this one out. The unified classification system, okay, and sorry. And the other classification system. So let me walk you through the unified classification system. For the unified classification system, remember with that 0.75 millimeter sieve or 5 micrometer sieve, okay, anything that passes that is clay or silt, fine grain. Anything that is retained in 75 micrometer sieve is either gravel or sand. So that's the starting point. Okay, we'll plot the distribution and do also the ArtBook limit tests. Once we do the particle size distribution and the ArtBook, that's the starting point. All right. So then we're going to read that going from left, going right. So start the okay. It's more than 50% retain 75 micrometer sieve, or it's more than passing 75 micrometer sieve. If more than 50% is retained, then it's coarse grained. If more than 50% is that it's fine grained. So if it was coarse grained, then we'll draw a line. We have a line here. I'm gonna get this one out. I'm gonna work only on this top. And then I'm gonna go next. I'm gonna go to sieve number 4 with the micrometer sieve. Okay, it's more than 50% retained or more than 50% passing. Okay, if more than 50% is retained, okay, then that becomes gravel. Gravel becomes the most the constant that is okay. All right, and then I'm gonna go now and check the percentage of fines here. Okay, was the percentage of fine less than 5% or percentage of fine 5%? Okay, if it was less than 5%, then we had to I had to get the coefficient of uniformity and the coefficient of curvature, right? Let's check if coefficient of uniformity is greater than 4 and coefficient of uniformity it's well below the gravel. If the coefficient okay, now if the percentage of fine was 12, then we have to do ArtBook limits for this. And then if it was classifying above the U line to ml, Below the U line, it was CL or CH, and then that becomes either silted gravel if it's below it's clay gravel. So both the particle size distribution have limits. Okay. Now, if it was less than 5 and fine, there was no need of Atterberg limits. So that means that the fine particle size does not have significance on the behavior of the soil. But if the fines are more than 12, a lot of it has significant behavior on the soil. Now, for the fine grain portion, let's see the portion. Okay. Portion, let's say, okay, that more than 50%, 70 micrometer silt. Okay, it's either silt or clay. We know that silt is clay, and then silt and clay, liquid less than 30% and liquid fluid more than 50%. Okay, if it's 30%, then we talk about here. We talk about plasticity, high plasticity. Okay. Right. Now we go. It can be either organic or inorganic. All right. For inorganic, we would need to do extra tests of drying. Okay, but mostly we deal with organic. Oh, sorry, inorganic, not organic. Now for inorganic, we'll check P is greater than 7 and plots above the A line. That is PI less than 4 and plots the A line. That's silt. Okay, that's silt. So the process just follow slowly and do their ArtBook classification. That is the group soil plus soil name. Let me pick question from you. Question. Question from you, ladies and gentlemen. Pick a question from you. I'm waiting for a question. Question, ladies and gentlemen. Kole, I think if you raise up your hand, I'll be able to. All right, Kole. Raise up your hand.
Maybe I missed it. Did you mention what the MH or OH, ML and OL stand for, and CL and OL?
I did mention that. Okay. C means clay, L means low, M means silt, L means low, O means organic, L means low, H means high. Okay. So CL will be clay of low plasticity. ML will be silt low plasticity. O will be organic of low plasticity. C will be clay of high plasticity or fat clay. Okay. Clay high plasticity is fat clay. Clay of low plasticity is clay. Okay. CL is silt of plasticity. Oh no, ML is silt of low plasticity. So C means clay, M means silt or organic, G means gravel, W means well, means gravel, P means poorly. Okay, so G, so you know G, C, L, O. Okay, let's say G, S. Sand, clay. No, let's say okay. G is gravel, S is sand, C is clay, is organic. Okay. L is low, H is high, low, high, and then W is well, is well. GW is well graded. Okay. G, okay, is silty gravel. GP is poorly graded. GC is clay gravel. Make sense, Humphrey?
Yes, sir. Thank you very much.
All right. Any other question? I think Step was trying to. If you just raise your hand, I will be able to. Right. Anybody the question? Okay. Do an example and see. Okay, let's see. So let's try and see if we can do unified classification. We have done article size distribution, then picked a portion that percentage passing sieve number 4 is 82, passing sieve number 10 71, passing sieve number 64, passing sieve number 200 is 41. 200 number sieve is a 0.075. Okay, so 41% passing. So in other words, it's than 50%. More than 50% is retained. If 41% passing, then 59% is retained. Okay, right. We're gonna go. Let's go back to this. Okay, more than 50% retained. So we are here. So we are here. So we get this one out. Okay, and then we are going to sieve number 4. Okay, sieve number 4. Percentage passing 81, so that means 18%. 18% is retained. Okay, it's retained. Then 82% is passing. Okay, so let's see. So that means we'll come here and see that it's right here. Let me just clean up this so that we don't have a messy board. Okay. We already said this. Yeah. Good. And then we came here and say it's 18% passing. So not this. So it's here. So next we want fines. Is it 5% fine or 12% fine? So fines are 41%. It's more than 12%. It's not this. So we go with this. So 12% fine. So class HS, we need to go to ArtBook limit and check this. Liquid limit is 31. This is the index is 12. So we're gonna go that 12 and 31 is around here. Okay. Just check clearly. 31 is around here. So it comes to CL. CL right there. Okay. So it's clay, it's sand and clay. All right. Sand and clay. So then we have percentage passing silver that we're gonna have like there's a gravel, the sand portion and the clay portion. So clay is about 41%. Sand is about 18%. No, sorry, gravel is 18%, and then the remaining here is okay, to close to 40%, maybe 40%, I don't know, 42% or something. So it's clay, sand with gravel. That is the name of the soil. This is where it is, right here. Clay, sand. But then don't ignore the portion of gravel because there's a portion of gravel in it. Okay. So the other classification system is the ARCH system. The ARCH system. Let's see how the ARCH system go about. In the ARCH system, work and classify soil from left to right. Okay, we classify the soil as A1, A2, A4, A5, A6, 7. Now, A1 is classified as A1A and A1B. A2 is classified as A24, A26, A27. Now, in the classification, as we go left, okay, the quality of the soil to use becomes worse and worse. Comes worse and worse. Now, this area for go ahead, Humphrey.
Please repeat what you just said about what happens to quality as we go left.
As we go left, as we go towards from A1 towards A7, the quality of that soil for use as a highway depreciates.
For use in a highway?
Yes, as for use as subgrade material.
Oh, subgrade. Okay.
Become the quality depreciates.
Okay, thank you.
Okay, now let's see. This is the criteria use. We would see how much passes sieve number 40, sieve number 10, for 40, sieve number 200, and then use liquid PI. Okay. For each and every class, knock out. If it doesn't qualify. If it doesn't qualify based on what is contained in sieve number 1, number 40, number 200, or the ArtBook limits, it does not qualify for that particular class. So let's knock off one by one. Let's see. Okay, let's do an example. Okay, we have soil. You classify PI, sieve number 40, is that, sieve number 10 is that, sieve number 40 is that, is that, okay, and the liquid limit and the plastic index is that. So we want to classify this soil. Let's go. Okay, we want to start with A1, sieve number 10, 50% maximum passing. Okay, 50% maximum. Okay, so it'll be more than 50%. All right, so let's see this soil. Sieve number 10, 50%. Okay, sieve number 10, 80%, 87% passing. Does it qualify? A1. Does it qualify? Let me just close this because some of you are going to use this to get the answer. Let me just knock off that. All right, that's sieve number 10, 87% passing. Sieve number 10, 50% maximum. So 80% than 50%, right? So it doesn't qualify to get that out. Let's go into that. 40, sieve number 40, 50% maximum passing. All right, let's see. Sieve number 40, 65%. So sieve number 40, it's 50% maximum. It does not qualify. That A3, 51% maximum. Sieve number 40, 51% maximum. Okay, it qualifies that. qualifies that. Sieve number 200, now sieve number 200, 30%, is not qualified. It qualifies here, but does not qualify here. A24, let's come to A24. Okay, let's go to sieve number 200, 35% maximum, 30% here. So it qualifies. Yeah. Next, we will go to liquid limit and plastic limit. Liquid limit, 40% maximum. Plastic is 10% maximum. So liquid is 22. Okay, and 40% maximum qualifies. And plastic is 8, 10% of maximum, 8 qualifies. Okay, 8 qualifies. Okay, so it qualifies 4. So the soil is 824. Based on that particle size distribution, it's 824. Now, with the ArtBook classification, we also need to determine what is known as the group index. Okay, and the group index is determined given that formula. So F200 is percentage finer than sieve number 200. Give it in percentage. Don't give it as okay. If it's 35%, 35%, or if 100%, put 100%. So the group index is given by that formula. That's the plasticity index. So then you need to calculate the group index. If you find a group index as 5, you round it to 4. If you calculate group index of 1, it's 0. Okay, put it as 0. So you have the ArtBook number. Let's say it was 824. Also calculate with the group index and put the group index in bracket. Whatever you got. Okay, you will calculate the index based on the relation given these three values. Calculate the group index and put the group index. Okay, put the group index in bracket. Then, the bigger the group index, the poorer is the soil. The poorer is the soil. Okay, is that percentage of F20 or more, liquid is high, plasticity index is high. So that if the group index is 20, you need to cut back the group index to a reasonable value. So is either mix the soil with another soil, okay, to find that is called mechanical stabilization, or cut back the PI or the liquid limit using lime, called chemical stabilization of the soil, okay, to bring the group index to 20. Does it make sense? Does it make sense? But
Please repeat that whole thing for group index, please.
Okay. The group index goes together with the ArtBook classification. Okay. Now, the group index is determined from that formula. Here, we have percentage passing sieve number 200, limit, and plastic limit. Okay, told you that a group index of 20 or more, very poor subgrade material, very poor material. Okay, so you want to make this material sub. 3 things are here. F20 percentage number 200. If you want to reduce F20, you need to mix that fine grained soil with coarse soil. That is known as the mechanical stabilization of the soil. Okay. Now, if you reduce I or liquid limit, you need to solve them. So that's lime stabilization. So that's the of lime stabilization, you're reducing the liquid limit, the index of the soil. Okay, so you need to have a group that is as low as possible. Now, if you calculate the group index and get 3.5, round it to the nearest and put your. If you calculate a group index and get a value of -1, okay, put 0, right? So above 20, group index above 20, that soil is not good for it becomes so poor for subgrade material. Humphrey, did you understand?
Yes, just sorry, one more question, because you broke when you were saying what if you want to add the liquid limit and the plastic index. You said we do add lime or?
Yeah, do you know the essence of lime stabilization? You did stabilization in third grade. Sorry, in your third year.
Yeah.
Did you do soil stabilization?
Yes.
What are the three soil stabilization?
We had mechanical, we had chemical.
So what's mechanical stabilization?
Mechanical stabilization was done things like compaction.
No. Compaction is not mechanical. Okay. Stabilization of the soil. Okay. No. Compaction is not stabilization of the soil. Okay. Compaction is densification of the soil.
Oh.
Stabilization is to improve its property.
Sorry?
Stabilization is to improve property of compaction. Compaction is densification. Okay. So you had mechanical stabilization, which is called mixing two soils. Thing affecting the group index here, one of the things is F20. The soil are finer, passing sieve number 200. So you need to F20 adding that soil with granular soil.
Oh,
The other thing affecting here is the liquid limit and plastic index. You need to pass liquid limit and plastic index by adding lime to that soil. Okay, lime contains what? Calcium. Okay, and F20 clay contains sodium cation. There's an exchange.
Sorry, I lost you a bit. You broke. I didn't hear what you were saying. You said calcium carbonate.
Yeah, let me just put it simple. When you put lime in the soil, you will reduce the liquid limit and plastic index. Yeah. Read more for yourself. You'll be able to understand.
Okay, thank you.
Yep. Any question, ladies and gentlemen? Any question, ladies and gentlemen? Okay, that's a question. Anybody the question? Any other person with a question before we proceed? Okay, here's a question in the public chat. Let's see. Yeah, okay. Mechanical stabilization is the addition of materials. Graded material you are using 20. Round of GF to the nearest G. If you had a number like 3.7, that's 4. 3.2, that's 3. -1, that's 0. All right. Okay. That must be enough fun. Okay. Any other question? Any other question, ladies and gentlemen? Any other question? Okay, let's do phase index. Okay, again, okay, soil in itself contains three things. Contains the solids, contains water, contains air. So the solids are not compact, they are void between them. And those void spaces contain water, air. So you can idealize any soil using a phase diagram. We have air, water, solid. All right. In terms of mass or in terms of volume. So in terms of air as of 0, water as a mass of mw, and soil solid as a mass of ms. So the mass of water and mass gives mt, the total mass. The volume of air, volume of water, and volume of solids are also there. The volume of air and the volume of voids. Okay, and then the volume of solids. So the solids and the volume of voids become the total volume. Okay, now we have something that we need to define, the void ratio, which is the ratio of the volume of voids to the volume of solids. Void ratio to infinity. Okay, dense to very loose. Dense to very loose. The porosity N is the ratio of the volume of voids to the total volume. Ranges from 0 to 1. Now, the correlation between the void ratio is given by these two equations. Okay, let's define another thing, the degree of saturation. Okay, the volume of water in the void spaces. So the ratio of the volume of water in the void spaces is the degree of saturation of water. Now, if volume of water over volume of, if the soil, the void is filled with water, then the degree of saturation is 100%, so that's a saturated soil. If the volume of water is 0 in the void spaces, that's a dry soil. In between dry and saturated soil. Now the specific volume is the volume of the void ratio. Let's take it out from the void ratio. Let me not explain all. The specific gravity will be the mass of solid of the same volume of water is termed as the specific gravity given by that formula. Okay, you put from basic soil mechanics, from basic mechanics. Now, okay. I talked about other things as water content, the mass of water to the mass of solids. Now, determination of water content in the lab, that's easy. Just, you take dish, get its weight M1. Dish and wet soil, put it in an oven for 24 hours at 105 degrees, get 3. So this is dry. So M3 minus M1 is mass of sources. Now, M minus M2 mass of water. So mass of water, mass of solids times 100 gives you the content. Yeah, easy. You did this in third year. Even from the picanometer test, okay, to we go to picanometer test, 50 millimeter or 100 to 100 millimeter picanometer test. This is for coarse grain. This is for okay. So you'll need to get the mass of the empty jar, empty, mass of the jar plus dry soil, M2, of the jar plus dry soil plus water inside, and M4 is the mass of the jar plus water only. The specific gravity is the mass of the soil to the mass of the equal volume. So work all this formula, you get that. That's follow this example, you'll be able to calculate the specific gravity. Let me get some water. Give me a second. All right, okay. Then let's do some relationship between the phases. We said that the void ratio is the volume of void, the volume of solids. By the way, let me take a question before we proceed. Let me question. Before we proceed. Question from you, ladies and gentlemen, before I proceed. Is everybody following? At least type something for me, yes or Y or N. Y means yes, N means no. All right, that's good. Quite a good number following. All right, very good. Okay, okay. So given by that, we can say that void ratio is the degree of saturation is volume of water or volume of water. So volume of void is volume of water of saturation. So then if we bring this to this here, the is given by that equation. It's combining the equations. Then volume of solid is mass of solid over the density of solids. Volume of water is the mass of water over solid, so density of water. So then volume of solid is here, volume of water here. We want to combine these two, makes it degree of saturation is 1, E, mass of water, mass of solid, density of water, density, solid density of water. What is this? Is the water content. What is the density of water? Is the specific gravity. Therefore, the degree of saturation of a soil is the water content, specific gravity, or void ratio. That's the formula. Is it making sense, ladies and gentlemen? Okay. Let me punch in a couple of things. There are volume indices that we need to define. Okay, the bulk of the unit weight, total mass over total volume. Total mass is this over total volume. So that brings us to rearrange things from the first diagram. The density is by specific gravity, density of water, 1 plus content, 1 over E. Or you understand that the water content here, water content will be degree of saturation E over GS. So if you arrange that here, you'll get the same equation here. These two equations are the same. So expressed in a different way. Okay, that's one. B is the saturated. Look at this equation right here. Let's bring that equation right. Okay, saturated density. That means the soil is saturated now. So S1 is 100% or S1 is 1. So put that 100% there. So that the R is the saturated density. Okay. Saturated density is the saturated density as the water. So in other words, the soil is submerged. Okay. What will take the pressure is the soil skeleton. Subtract that from the water. So it's saturated density minus density of water. Okay? Rearrange things, that gives you the final equation. The dry density. Okay, that means there's no water, 0, and the water content is 0. Okay, so the dry density, if you come back to this equation here, let me just clean up the board. Equation here, water content is 0. We don't have that, so it's GSW and that. Okay, water content is 0, so that gives you the dry density. So in other words, the bulk density is the dry density. So that the dry density is the bulk density over 1 plus the water content. Question? Any question? Are you following the lectures? The table I provided here will give relationship. Given certain parameters, you're able to, work around your density. Is it something that you learned in soil mechanics 1? Chomba, or who is this Chomba? Is this something you learned in soil mechanics 1? Okay, anything new from soil mechanics 1? Whitney, anything new from soil mechanics? Anything new from soil mechanics? None. So everything is new. All right, gone. Okay, that's another table. You can do some of these examples from the soil mechanics one, so everything is easy for you. Okay, everything is easy from soil mechanics one. Just do the example and follow through. Okay. Now, we say that soil, it's either granular or okay. Now, when we talk about relative density, we are trying to define the density of the soil. Okay, density of the soil. So relative density, when we compact the soil, okay, no, any soil is at its natural density, compacting without loosening. It has its natural density. You compact it further. When you compact it further, the void ratio becomes smaller and smaller, so that's the minimum void ratio. If you loosen it, you become the minimum void ratio. If you loosen it, the void becomes bigger, so that becomes the maximum void ratio. The density state in between the loose, okay, between the loose, natural, and the compact state by one at the relative density of that soil. So the relative density that defines whether it's very loose to dense soil. That also at loose state, it corresponds to minimum dry density. At dense state, it corresponds to minimum dry density. Okay, and its natural state, it corresponds to a certain dry density. So that can also be defined in terms of dry density and also in terms of the void ratio. Okay, everything right now is completely neutral. Okay. So let's see. Let me get to soil compaction a little bit. Yes. Okay. No. That I don't think I should have had that. Yeah. Let's keep that. Talk about soil compaction a little bit, just a little bit. Do I even need to talk about soil compaction? Talk about advanced soil compaction. Let me talk about soil compaction a little bit, just to refresh in your mind. So, compacting soil, we densify the soil by the air void through the application of mechanical energy. So we know the areas that we use soil compaction for highway, dams, and many engineering properties. Why do we compact soil? Why do we compact soil? Let me ask somebody and yourself and talk. Why do we compact soil? Why do we compact soil? Can I pick any names? Benjamin. K. Benjamin. Why would we compact soil for that is the bearing capacity? Why then would we compact for embankments? For embankment, why would we compact? Okay. Okay. Yeah, we can increase strength, yeah, bearing capacity. Okay. Okay. For embankment, yes, we increase the slope. Okay. What about for dams? For dams, why would we compact the soil? Yeah. Okay. For dams, no, yeah, hydraulic conductivity, yes, we want to reduce the conductivity because we want to avoid seepage through the dam. And we also want to increase the shear strength of the system. It's a slope. That slope can fail within shear. Okay. All right. So those are the reasons for compact soil. Okay. Yeah, reduce seepage. When you reduce seepage, reducing the hydraulic conductivity. Okay, reduce seepage or reduce the hydraulic conductivity. So you're reducing the seepage. Now, the various factors that affect the soil. One would be the type of soil being compacted. Okay. It's easier to compact soil. Okay. It's easier to compact the soil than it is to compact fine grained soil. Method of compaction. Okay. Probably using a ship foot roller or it's different than would you, when you use the compactor. Compactive effort that has to do with and also the moisture of the soil. It's easier to work on light moist to dry soil than working on very wet soil. So that's the degree of compaction. So we have two methods: standard and modified. Standard, yes, you compact in 3 layers. The weight of arm is 25 kg, 2.5 kg. Drop height is 3 layers. Modified to 5 layers. Blow per layer is 25. The weight of the arm is 4.9, being 157.2 millimeter. So then the compact effort in standard modified the compactive effort in standard. So let me ask, why the difference between okay. What do you think is the reason for separate hammers? Raise up your hand, I'll unmute you and let you talk.
Could you please repeat your question?
I'm asking what would be the reason for using different hammers? Okay. Humphrey, you've talked too much, man. Let the other people talk. Okay, Humphrey, go ahead then. Oh, one more time, Humphrey, just raise up your hand, raise up your hand. Raise up your hand. Let me unmute you. Okay, go ahead. Now unlock your.
I think it's we use different hammers to represent the different types of compactors with different weights or vibrations that we can use.
Okay. But we can also use standard, which is the low compactive effort, to replicate what will use your drum roller. So let me ask you, I'm building road and I'm building a ramp for planes. Okay, both connected. Okay, which one do you think I'm able to produce the moisture density relationship using the modified, and which one do you think I'm likely to use standard?
Honestly, sir, I haven't had the question again. The breaking is very bad right now.
Okay, what I'm saying is this, okay? If I want to build, okay, in a residential area, if I want to run in JKIA, I have another one, JKIA. Which one do you think I'm going to use more, and which one do I think I'm going to use standard? Go ahead.
I think for areas where you're going to, for areas where you expect heavier loads, you're going to use the modified, and the ones that are just regular loads, we are going to use the standard.
That's the thing. That's the thing. So in other words, if I use standard, I'm to use more compactive effort. So there would be the higher density as typed in by Kahura. Okay, the higher would be the maximum dry density. So in other words, my target is to be higher. That means if I have to work on material, then I'll be using very high compactive efforts. Yeah, very compactive on that. Either give it a lot of passes to target. All right, let's see. The quality is something that you understand how compaction is done in the video. So we would define the compaction by compaction curve, maximum dry density, and the moisture content. Okay. Now that's the compaction in the field, in the lab. In the field, we will define the density, which would be a certain percentage of the maximum density. All right. So let's have a look at that. Now, we will have, okay. Okay, let me see how to present this. That we may understand the compaction curve with zero air void. Zero air void. Remember, we say the dry density will be the GS water 1 plus A. Ratio, it is that that over E. Okay. Zero air void means the saturation is 0, okay? Sorry. Is WGS over SR. You substitute here, we get that, the okay? So the zero air void means the soil is saturated. That will be given by that. So then we'll get different water content and plot that line. That's the market line that will never achieve that. Okay. Now, my question is, if you compact soil in the field, okay, you compact the soil in the field to certain dry density, let's say 90% dry density, and then it rains in the field. It rains in the field, the soil becomes saturated. The water content of that soil in the field. Are you able to determine that? Are you able to determine that? What would be the suppose? Okay. That's the dry density moisture curve of the soil. My target density is right here. Now that's the target density. Okay. That's the content here. Okay. It rains. And the soil becomes so much saturated. I can estimate the water content of that soil. To give it a try. Anybody? Are you able to estimate the water content when the soil is packed? Are you able to estimate the water content when saturated? Are you? Let me get some reaction. Are you able to see the zero air void right here? Okay. This is the maybe 90% degree of compaction. If this line to the air void there, this is the theoretical that if you bring that down, that is the water content of the soil. You compact the soil in the field, but not saturated. When it will saturate at that water content. See, that's the reason we have those things. Does it make sense? If you compact it to the maximum dry density, for it to saturate, bring it here, type them zero air void. And it's down here. That's water content. It is completely saturated. Okay. Let me pick question for me. Any question for me? Any Any question, ladies and gentlemen? Okay, let me also pick something. Okay, maybe I wouldn't go much in that type of compactors. Where would you compact for small? Just use those big compactors, so you use handheld compactors. You would the place the lab. Okay, usually we define 95% of the maximum dry. Okay. Usually 95% of the okay. For control, how do we know that whatever we compacted is achieve that target? We use a couple of methods: rubber balloon method, and nuclear density method. For sand cone method, you dig a hole, you compact it, dig a hole, get the weight of the soil. You need to determine the and the water content of the soil. So weight of the soil, volume of the hole gives you the bulk density. The water content of the hole gives you the dry density. Compare this dry density got here to the from the lab. That will be the relative of the soil. Now, how do we get the volume of the hole? We replace with the sand. We will know the volume of the sand. We use that because we know we have the jar. We'll replace the sand of similar weight here and then get the volume here. Okay. For nuclear density gauge, nuclear density has two main radioactive substances there. American 137 and I think cesium 240 something. One is the hydrogen content, which translates to one will measure the dry density of the density of the soil. So water content divided by that will give the dry density. You're able to the relative compactness of the soil. Follow that example, understand how the method works. Okay. All right. Any question to the method? I'm just going through a few things for you to I don't know what time is it now. No, but there's something you're trying to ask. Are you able to do it yourself? Ask that. Chomba. Just and to unmute you, and then you're going to ask the question. Chomba, just raise up your hand. Okay. I've unlocked you. Now go ahead and unmute yourself. Question. Chomba. Go ahead. Chomba, go ahead. think you can talk. You're muted, unlocked, so you can. Yeah.
Hello.
Yeah, go ahead, Choma.
Oh, I was trying to ask whether you can repeat the concept you're explaining for addition of moisture content beyond MDD.
Not additional moisture content. Okay, you've compacted the soil in the field. Compact the soil in the field. Okay, and let's say that it rains, so the soil becomes saturated. You're able to put the moisture content of that soil. Under ideal situation, that's what I was explaining. Draw a line to the level of compaction achieving and the moisture content. Draw a straight line to estimate the moisture content in of that soil.
Oh, okay.
Yeah. Yeah. All right. So, let me see what's remaining here. Permeability. That would be interesting. Yeah, I mean, I think there's something that I had a day that I didn't even want to teach about. I think I want to build this shear strength thing. Let me do permeability. Then your next slide for stresses in soil mass. That would be important. All right. Let's talk about permeability. Okay. I'll be able to pull in new things probably you didn't do before that might be helpful. In soil, there are dead spaces. So those void spaces form paths for water to flow. Okay. Now the water will flow from high energy to point of low energy. Okay. So in other words, energy to low energy, there must be head difference. Perfect. Now, the thing we need to determine from soil the hydraulic conductivity or the coefficient of permeability. Now we say that water flows from high energy to low energy. Okay? There must be head difference. So there is the pressure head, the velocity head, and the elevation head. Now, if it's horizontal, the velocity head is usually small. We through the soil, so we have the pressure head and the elevation head. So that if we have a soil column, and we have a piezometer, okay, piezometer or standpipes. The piezometer, they are used just to measure the water column level. Okay, so if you have through a medium, we have piezometer here and another piezometer here. Taking these points that they the piezometer, we take that as the elevation A. Bottom of this piezometer is B, ZB. Now the water is flowing. The piezometer is going to measure or indicate a water level. So that water level, the water over the density of water gives you the level H1. This other piezometer will read the water level here, H2. So the total head, point A will be ZA plus HA total head at point B will be ZB plus HB. Now the difference between total head at point A and B will be delta H, as the difference is all readings. Okay, all right, different in reading. Now this difference in piezometer reading is the head difference. Now that head difference over length between the length between the two columns will divide to the hydraulic conductivity. So the hydraulic gradient. Delta H over between them. That gives you the hydraulic gradient. Let's put a couple of things, okay? That is law of water through a medium, okay? It's given by K times the hydraulic gradient. K is the coefficient of permeability. Okay, coefficient of permeability. We can determine K from the lab, two method, and from the field. From the lab, we use constant head and falling head. From the field, it's wet pump test to determine coefficient of permeability. For the head test, constant head test, we have a column of water, okay? Saturate column of water, keep this head constant. We've kept this head constant. We continue pouring the water. So we have where the outflow is. We will stop, measure the time as the water is free in the cylinder, right? In the cylinder. So we know the volume of water that fills the cylinder over the time. That gives you volume is meter cube over time second. That will give you the quantity of seepage in whatever meter cubed or centimeter cubed second. Okay? All right, that would be the same as the area times the velocity times the time, okay? Such that the I, the hydraulic gradient I is H. Okay, the head difference between this reservoir of length, hydraulic gradient, okay? Put that into the velocity portion, we get Q is K H L over N times T. So the hydraulic gradient Q volume, okay, I'm sorry, they use a notation. Use a different notation, volume Q times L, the length of the solid column, area of the solid column, head difference, and time. That's like so that's the same. That's the hydraulic falling head. Okay. Remember, you have a standpipe, and that standpipe is flowing inside here until it's saturated. So you are H1, initial H1, H2 is the final H, and then the change in H in between. Okay. So integrating from the small area to big area. Okay. So you see, quantity is Q, L over H, sorry, L over L, solid column times the area of the solid column. That is the same quantity that through the small pipe area, okay, H over dt. So you'll integrate in between the H over dt from H1 to H2, from H1 to H2, and then ultimately, just if you remember slowly, that will this value or this value in, so that will be the constant head. What you need to do is H1 and H2 time from 0 to the time that you reach 2, and then the area of the small standpipe, the area of the large standpipe. That's what you need to know. Okay. Now, those are the examples you can go to follow, because this is just review, so I'm not spending too much time. Now, this should be new to you. So I don't know, maybe you learned this, but let's see. We say that the head, total head, is the pressure head, the head, elevation head. We say the velocity head is small. So the total head is the head plus the elevation head. Right? Now, suppose water is flowing through this soil. Right? Flowing through this soil. Are you able to get heads between point A, C, D? Let's see, for example, okay, pressure head, okay, with respect to a datum. If we have a datum here, when we inside water, the head going down becomes positive. Okay? At the surface of the water is 0, atmospheric. All right. So I want you just to follow slowly, because follow slowly this. At point A, what is the pressure head? At point A, what's the pressure head? Let me get somebody to speak. Men are not speaking, ladies are not speaking in the class. Let me see if I can pick. I can differentiate ladies' name. Okay. Ivy Getanda. That must be a lady. Let me say another one. Karime Anje. That's another lady. Let me see another one. Mary. That's another one. Dola Michelle Adhiambo. That's another one. Moro Sherry Faith. There's another lady. Okay, those 5 ladies. You can raise your hand. I'm going to unmute you. Let the list know. And I've talked a lot. Just raise your hand. Then I'll Ivy, Karime, and you know, the other ladies that I called. Raise up your hands, guys. Ladies. This portion, I think, will be difficult for me to get people. All right, ladies, raise up your hand. Let's say at A, what is the pressure head at this point A? What is the pressure head? What is the pressure head at point A? Anybody willing to answer? What is the pressure at the point? What is flowing down here? Your piezometer measure the pressure. Ivy Kitanda. Okay, let me unmute you, Weibo. Listen, Nixon. Go ahead. web.